All right, so speaking of the extra bonus assignments, a couple of things I want to do. We'll get to the social media professional development assignment number 3 for this week. But one thing that I want to draw your attention to is the innovations and suggestions survey as a little bit extra this week. So as we're going through the social media professional development, as we continue to collect the innovations and suggestions, and that's so far been a really a big success. The time has come where I need to make a decision, what is this actually going to be worth? So I keep thinking about different options, different amounts, what are the bonus points actually going to be? So in this week's survey, what I'm asking you to do is, if you have any ideas about what would be motivating and fair for the innovations and suggestions, and what would be motivating and fair for the social media development. Just let me know what you think would be a good system for the bonus points. So what I mean by motivating is that I do want this to be rewarded in this classroom by an improvement in your final grade. So I do want it to be motivating. I do want people to say, you know what, I am going to do this because I would like to earn these bonus points. So it has to be something that would be motivating to a student. On the other hand, though, it also has to be fair. So something that would be unfair would be something like, well, if you do one of the assignments, you get 100% in the grade. That would be completely unfair to any student who decides not to partake of this assignment. So it can't be so huge as to undermine the fairness of the course and the fairness of any of the other evaluations. I don't want it so small that students are not motivated to participate. So I'm not a student. I don't have that sort of firsthand experience. So that's new in this week's survey. I'll keep it in this week's survey, maybe next week's survey, depending on the response. So if you have any ideas on what you would like the bonus points to be, what you think would be something that would be motivating and fair, please let me know, and I'll consider everybody's and make that decision very soon. All right, so that's for the innovations and suggestions for this week. For this week's social media professional development assignment number 3, what we're going to do is we are now going to talk about one of the benefits of doing this and getting plugged into your network. I mentioned this before, but this is often known, and I like to call it as the big ask. So the big ask is when you ask your network, when you ask your connections for some help, for some personal or professional help. So for example, one of the people that I follow, this is from last year, tweeted this out and goes, academic friends, what is the best writing advice for undergraduate who will be writing their first APA style manuscript this semester? I would like to give them tips and tricks from the pros, that is you, please and thank you. So they sent this out basically because they're teaching, probably for the first time, a new course, the course that introduces APA style to their students, basically P211 here at IUSB. And rather than them going through hours and hours of reading and articles and other resources to try to find the best practices, they just said, you know what, I'm going to plug into my network and see what they've done, see what experience has taught people. Why don't you very quickly tell me what the best practices are, tips and tricks, so that they can incorporate that. So that's a big ask, right? You're going out there and you're basically saying, hey, can you do some of my work for me? Really is what this boils down to. Can you do this for me? Can you take time out of your schedule, to do this for me? And it is completely fine and encouraged to do this. This is one of the reasons why you want to get plugged into a network. But importantly, you want to give before you take. You want to contribute before you ask. So if you take a look at Randy's Twitter feed, you can see that he has produced a bunch. He's already contributed 2,200 tweets to his community. He has given this much content to the community. So when he finally says, hey, can you help me out? People know him, they feel very comfortable, they don't feel put out, they basically think to themselves, either consciously or unconsciously, hey, I've read a lot of his tweets and he's posted a lot of things that are helpful. Of course I'm going to help him now when he's asking. So that's where we want to eventually get. So one of the ways that you can contribute very, very early, right? So you might not have any original content to contribute. You might not have any articles that you publish where you can say, hey, take a look at this great new article. Here's a link to a talk that I gave. However, one thing that you can do is you can help spread other people's influence. You can help what's known as amplify other people's voices. And you can do that very simply by retweeting. So for example, when I saw Randy's tweet, I retweeted it, some great advice in this thread, and basically that amplified his voice. That was a contribution to him. It contributed to my students as well, who now got to see and read through his thread for tips on how to write their papers. So that was one way to contribute very easily, very simply, and especially when you're a beginner in a particular field. So for this week, what we're going to do is you are going to retweet any 2 tweets from the 5 psychologists that you're following. So last week you found at least 5 psychologists to follow. They'll be active, they'll be tweeting out information. This week what you're going to do is you're going to just pick 2 of those tweets and you're going to retweet that information. So you're going to amplify their voices as your contribution to that network. So when you're retweeting this, no comments are required. You can just hit that retweet button and it'll ask you retweet with no comments or retweet with comments. So you can just retweet it with no comments required. But if you do want to comment, then I uploaded a PDF, the do's and don'ts of networking online. Make sure you read that first before you write anything, because there are some do's and don'ts about what you should write. And again, we're trying to make this professional media presence for you, social media presence for you. So we want to make sure that it's clean. We want to make sure that 5 years down the road, you don't have to go back and look for tweets that you want to get rid of. So if you do want to retweet and comment something about it, write a little additional information, please read that first. And there's a short little series of do's and don'ts, and make sure that you adhere to that advice. So that's what is going to be the assignment for this week. And then the way that I'm going to track this one is that you're going to use the hashtag FuturePsych2019. So that's the way that I'm going to track you on this assignment. So once it's due, which is Monday, October 14th, I will go online, I will search for that hashtag, and I will see your name there, and you will be given points for completing this assignment. All right, and it's due this Monday by midnight. Any questions on assignment number 3?
So we have to at least comment that hashtag if we're not.
Yes, actually that's a very good point. Yes, so you don't have to comment anything, but do make sure that you write the hashtag in there so that I can track your involvement. That's a good point. Didn't even think of that. Any other questions? All right, perfect. So what we're going to be doing today is we are going to wrap up our look at Chapter 4. And I think we're actually a little bit ahead of of where the syllabus is. So we're going to actually have time to intro Chapter 5, which is our first look at hypothesis testing. So that actually kind of works out pretty well, because Chapter 5, that first look at hypothesis testing, can be challenging. So it's nice that we're going to get a first look at it before we have to launch into it full steam. All right, so Chapter 4, we're getting so close to doing the kind of cool stuff that statistics is used for in psychology. We're almost there. We're just laying down a little bit more foundation. But again, remember that the point of all this, the final goal, is to make psychology as effective as possible, to help as many people as possible. And the only thing that allows us to do a study on 14 students, 14 subjects, and help the entire population of subjects is the statistical skills that we're learning right now. It's hypothesis testing. That's the only thing that allows us to intelligently, ethically, objectively generalize our findings from a sample to a population. That's what makes psychology powerful. So just keep that in mind as we're working through this. That's our end goal. What we're going to do today is we're going to have a very quick recap on samples and populations. We covered that last time. Quick recap on distribution of sample means. And then we're going to cover the central limit theorem, a little bit of mathemagic that allows psychology to do what it does. And then it's going to be on to chapter 5. All right, so real quick recap. Samples. We use samples to estimate population parameters. We are almost never interested in the sample. We're interested in the population. We're never just interested in the 14 subjects. We're interested in the millions of people that make up the sample. And the challenge for us when we're estimating things about the population from your sample is that you never know where your sample came from in the population. So if you have a sample of 5 individuals, it might be these 5 individuals from the population, or it might be these 5 individuals from the population, and both of those would give you very different ideas about what your population is like. So that's our challenge, is that any sample we take from a population will have a sample mean that is going to be different every single time, depending upon who gets randomly chosen. So how do we know what that population mean is if we're basing it completely on the sample? And the answer to that is that we're going to use the fact that certain samples are more probable to come from a population than other samples. So a sample like this, if we were sampling people from the population and it was their IQ scores. So that population up here are the IQ scores for everybody on Earth, and that would be a normal distribution. Well, this sample here, where you get some that are below average, some that are above average, some that are in the middle, basically a kind of typical sampling, that seems to be a high probability sample. That seems to be like a sample you would not be surprised to end up with. On the other hand, a sample like this, where it's all extreme cases with high IQ scores, where your entire sample is made up of Bill Gates, is made up of Neil deGrasse Tyson, it's made up of Bill Nye, it's made up of Marilyn Von Savant, there she is, it's made up of Ruth Lawrence. That seems very unlikely. And it really is. It's highly unlikely to get samples that are that extreme. So that's what we're going to be using. We're going to actually be able to calculate the probability of selecting a particular sample from a population. And as soon as we get to probabilities, we're getting to proportions. As soon as we get to proportions, we get to a proportion of a distribution. And the proportion of the distribution that we're looking at is that distribution of sample means. The distribution of sample means is a very important concept, and it's one that is challenging because it's kind of like an inception style idea. So the distribution of sample means, it's named amazingly because it's exactly what it is. It's a distribution of sample means. But it's a little bit difficult to grasp mentally because it's a distribution of distributions. So this is your distribution of sample means. Each single point in this frequency distribution is not one person. Each single point in that frequency distribution is a sample that had a particular mean. So rather than being a distribution of individuals, this is made up of a distribution of sample means. And some of those sample means are very common, right? Because the frequency with which they occur is high. Some of those sample means are uncommon. The frequency with which they occur is low. Some of them are improbable. Some of them are highly probable. But this is a distribution of sample means. It's literally a distribution of all the possible sample means from a particular population. So each point is a sample with a particular mean. So it's not a distribution of individuals like we've been working with. It's a distribution of sample means. It's a distribution of samples. So the great thing about the distribution of sample means is that its shape is very, very predictable. So when you have, and this is the only time that this occurs, when you have a certain population distribution, right? So this flat distribution here, that's the population distribution for dice rolls, for single dice rolls. If you look at the history of every single dice roll ever thrown by man, this would be the distribution of those dice rolls. And if you have a distribution of sample means made up of sample sizes of 1, then what you have is you have a distribution of individuals. You have exactly the same distribution as the population. And that's the only time that that happens, when you have a sample size of 1. And that's why the book, the textbook you're using, was able to use a population distribution up until this point. Because if you remember on all your homework, they always mentioned a sample size of 1 individual, 1 person. So that's why they were able to do that. As soon as you go to a sample size of 2, your distribution of sample means no longer looks like your population distribution. So that's the distribution of sample means, the distribution of samples in a population. For 2 dice rolls, sample size of 2. That's what it looks like for 3 dice rolls, sample size of 3. That's what it looks like for 4 dice rolls, sample size of 4. That's what it looks like for 5 dice rolls, sample size of 5. And as you'll notice, it's starting to look a lot like a normal distribution. And we're going to see that that is no accident. And that's where the power of and the ability of psychology to help the millions of people actually comes from. So the challenge here, one of the things that we're going to have to figure out is that this distribution of sample means, I built this one by basically running an Excel program that generated every single outcome for 5 dice rolls. And then I put together a frequency distribution. And that's how I know what the shape of this distribution of sample means was. But that's not something that we can do in real life, right? We can't run an experiment where we test 20 individuals, and then as soon as we're done testing them, we throw them out and get another 20 individuals, and as soon as we're done testing them, we throw them out and get another 20 individuals, and we do this until we get every single combination of 20 individuals from the population. That would literally take billions of years to do. So we can't do that. We only have 1 sample usually. So how do we figure out this distribution of sample means if we only have the 1 sample? How do we put together all of these potential samples if we only have 1 sample from the population? And this is where the central limit theorem comes in. This is where the central limit theorem saves the day and makes psychology possible. All right, so what does the central limit theorem say? So the central limit theorem says that for any population that has a mean of mu and a standard deviation of sigma, the distribution of sample means from that population of a certain size, a size of n, will have a mean of mu, and it'll have a standard deviation of sigma divided by the square root of n, and then importantly, it's going to approach a normal distribution as the size of your sample, n, approaches infinity. So we'll take a look at that last part first. Okay, so that last portion will approach a normal distribution as the size of your sample approaches infinity. That's why we've been spending so much time working with that normal distribution table. That's why that normal distribution table is table A1 in your books. That's why we did going from a percentage to a raw score, going from a raw score to a percentage. It's because of that last part of that central limit theorem that your distribution of sample means approaches a normal curve as the size of your sample approaches infinity. And in reality, as it mentions in your book, As soon as your sample size is 30 or more, for all intents and purposes, your distribution of sample means is a normal curve, right? It's reached it. It's basically indistinguishable from a normal curve. And in reality, the number is much lower than that. 15, 20, depending upon your population's distribution, is usually enough to get you to this point. 30 is kind of like one of those accepted numbers. But just so you know, you don't have to actually get very sample sizes that are massive in order to make sure that your distribution of sample means looks like a normal curve. So how does this open up psychology? How does this make everything that we do possible? Well, first look at this first part here now. So for any population, that's important because psychology wants to study any population. We're interested in everybody. So we want to be able to study any population. We don't want to say, oh, well, we have Gen Z is now coming up, and I want to study the mental disorders that might be prevalent among Generation Z. We don't want to have to stop because psychology says, well, that population, we can't do that. Central limit theorem says any population. So any population is open. Every one of those populations will have a mean and a standard deviation. You can't be a frequency distribution without a mean and a standard deviation. So that means we can do it for anybody. The distribution of sample means for a particular sample size, which we will know, because we'll be doing an experiment. We'll say, well, I have 25 people in my sample. So we'll know how big the sample size is. And importantly, that distribution of sample means will have a mean that is the same as the population, and it'll have a standard deviation that equals the standard deviation of the population divided by the square root of the size of your sample. Now, why the square root? You need like a master's degree in mathematics to understand why is it the square root. Suffice it for us to do psychology, we know that it is the square root of the size of the sample. So just remember that it's the square root of the size of your sample. That is the standard deviation of this. It's the spread of this. So the mean of this distribution of sample means same as your population. The spread of your distribution of sample means same as the standard deviation of your population divided by the square root of the size of the sample. Size of the sample. And then importantly, this will approach a normal distribution. We know the shape of this even if we don't know the shape of the population. So we know the shape of the sample distribution even if we don't know the shape of the population because of this central limit theorem. So again, that's why we do so much work on this normal curve, because as soon as you have a sample in an experiment, as soon as you have a sample for a treatment, your distribution of sample means is a normal curve. It's a normal distribution. So that's why we put in the work before. And just to kind of show you the central limit theorem in action, we've seen it once already. If that is your population distribution, right? So we have a flat population distribution. There's your distribution of sample means for a sample size of 1. There's your distribution of sample means for a sample size of 2. So it's important, the distribution of sample means changes as your sample changes. Importantly, it no longer looks like the population. That's a sample size of 2. That's a sample size of 3. That's a sample size of 4. That's a sample size of 5. So for this flat distribution here, this flat population distribution here, once we get a sample of 5 from this distribution, we end up with a distribution of sample means that is approaching a normal curve. I mean, it's almost already there at only 5 subjects in this case. So we have a distribution of sample means that's approaching a normal curve, opens up the table, opens up psychology. We can help the population. What if your population distribution looked like that? So this would be like a dice where you colored in the side that had 1 die on it, and you put it so that it has 5. So you took a magic marker and you colored in 4 more dots. on the side that has 1. So now no sides have 1. You can't roll a 1. 2, 3, 4, and 6 you can roll one way, and a 5 you can roll 2 ways. What if that's your population distribution? Well, this is a completely different population distribution than the one that we just saw, right? It's not flat. It's got a different shape. And we, as psychologists, usually don't know what that shape is. We're usually unaware of what the shape of the actual population distribution is. But as soon as we start taking samples from that distribution, as soon as we take a sample from this distribution and say, I'm going to test a treatment, as soon as we take a sample from that distribution and say, I'm going to run an experiment, then we're no longer dealing with this population distribution of individuals. We're dealing with the distribution of sample means. We took a sample from the sample mean distribution. If our sample size was 1, then our distribution of sample means looks exactly like our population. That's why psychologists do not do experiments with just one individual, because you have no idea what your distribution of sample means will look like. But if you take a sample size of 2, take a sample size of 3, sample size of 4, sample size of 5, once again, we are getting very close to that familiar shape. This is looking more and more like a normal distribution, once again, only at 5 subjects. So it doesn't matter what this looks like, your population of individuals. As soon as you start taking samples by the mathemagic of that central limit theorem, your distribution of sample means starts to look like a normal curve. And it'll look like that regardless of what your population distribution starts out at. So if we have this population distribution here, where nobody scores a 1, nobody scores a 4, nobody scores a 6, once again, we might not know what this distribution looks like. And if our sample size is 1, we still don't know what our distribution of sample means might look like. But there's a sample size of 2, there's a sample size of 3, sample size of 4, sample size of 5. And this one, again, you can see it's approaching a normal distribution. And that's only after 5 subjects. You can imagine what this would look like after 10, 15, 20 subjects. It's going to be indistinguishable from a normal distribution. So that is why we're able to do the hypothesis testing that we're just about to get into, because for any population, any distribution of a population, it'll have a mean of mu and it'll have a standard deviation of sigma. The distribution of sample means for a certain sample size will have a mean of mu, so the mean doesn't change. The distribution of sample means has the same mean as a population, but the standard deviation will change. So you'll notice that the distribution gets squeezed in the higher the number of subjects, but importantly, it approaches a normal distribution and then approaches infinity. So just one more time, it gets squeezed in, and the shape it gets squeezed into is that normal distribution shape here. And the importance of this really cannot be overstated, because this is what allows psychology to investigate any population that it wants. So for example, if you wanted to do a study and you wanted to study the population of single fathers who have been diagnosed with mental disorders, right, and you want to do a study on their emotional quotient, right, what is their emotional intelligence? If you ask me, what is the population distribution for emotional intelligence for single fathers who have been diagnosed with a mental illness? I have no idea. Nobody has any idea, right? That data hasn't been collected. However, if you wanted to do a study on these individuals, as soon as you take a sample, as soon as you say, oh, I have a sample of 30 fathers who are single fathers and have been diagnosed with a mental disease, and I've tested them on their emotional quotient, what is the sampling distribution? What does the distribution of sample means look like? As soon as you tell me I have 30, I can tell you your distribution of sample means is normal. And as soon as you know it's a normal shape distribution, you can go to the table and you can answer questions about it. So we're able to do studies on single fathers diagnosed with mental illnesses because of this central limit theorem. Think about over the last, 2 decades, how many new populations have sprung up. So if you wanted to study gay marriage, if you wanted to study gay couples who are married, that is a category that literally did not exist, 2 decades ago. It's a very new, new population. But you want to do research on it. You're interested in it, right? It's psychology, it's behavior. You want to know what it's like. If you ask me, what is the distribution on any score? Let's say that we're looking at social anxiety. What's the distribution of social anxiety scores among the population of gay married couples? I have no idea. No idea whatsoever. But as soon as you say, oh, I have 20 married gay couples here, what's the distribution of sample means that they came from? I immediately can say it's normal. It's normally distributed because of that central limit theorem. And as soon as you know it's normally distributed, you can do the study, you can do the research. So that's one example. Another one, I remember that my student did this study in her senior seminar. She wanted to do a study on, I believe they're called connected bohemians. So if you want to know more about connected bohemians, you can learn about the Claritas prism. And what this is it is a list of demographics that marketers use. So it's an entire list of different groups of people. So pick up patriarchs, up-and-comers, home sweet home, big sky families, country casuals, white picket fences, pools and patios, traditional times, second city startups, young and influential, urban achievers, tool belt traditionalists, right? Bright lights, little city. These are ways that marketers identify different demographics, and they all have their different characteristics. And she wanted to look at connected bohemians. She wanted to look at these mix of young singles, couples, and families ranging from students to professionals all have one thing in common, being tech savvy. They're always the early adopters of the latest and greatest things. She wanted to do a study on connected bohemians. And if you ask me, what's the distribution of the connected bohemians on any particular score? I have no idea. No idea whatsoever. But as soon as you tell me I got 20 connected bohemians in my study, I can tell you distribution of sample means is normal. And that again opens up everything that we can do in psychology. So that's the power of the central limit theorem. We're going to get more into the nitty-gritty of the central limit theorem in chapter 6. But for now, just be aware that the central limit theorem is what allows us to do these studies. It's what allows us to figure out the distribution of sample means. And it's what allows us to use that z-score and that unit normal distribution table. That's what opens up the ability to do that, which opens up the ability to do psychology. All right, so any questions on the importance of the central limit theorem or what the central limit theorem, how it's going to be used? All right, so one thing I'll mention before we go to a kind of like final wrap up of this chapter 4, you might have noticed that I mentioned that we never know what the population is, right? We almost never know what the population is. And yet we are able to calculate the central limit theorem by knowing certain things about the population. So it's a little bit of a contradiction, right? We need the central limit theorem because we don't know what the population looks like, but we can use the central limit theorem if we know what the population looks like, right? That, if it's confusing you for the time being, don't worry about it. There is a technique that we're going to learn where you have no idea what the population is like, and you're still able to use the central limit theorem to calculate the distribution of sample means. However, as an introduction into hypothesis testing, it's much easier to introduce the concepts and introduce the steps if you assume you know the population. So we're going to start our look in chapter 5 at hypothesis testing with very rare and artificial conditions, specifically conditions where you know the population of scores that you're taking your sample from. Later on, we're going to be going more realistic, and we're going to drop that unrealistic assumption. So just if it's just in the back of your mind, and you're a little bit confused, wondering, well, wait a second, we don't know what the population is, but we can calculate the distribution of sample means if we know what the population is. Just know that we'll work around that when the time comes. It's just the sort of intro to this idea. All right, and to wrap this up, and this is an extremely important slide, we now have 3 different distributions that we're working with. And it's going to be to your extreme benefit to be sure that you can distinguish those 3 frequency distributions from each other and be rock solid on what each distribution refers to. So, for example, we've been dealing with this one for a while. We now have a population distribution. This is the distribution of scores from the individuals in our population. Right? So this is the population distribution. It has a certain mean, and it has a certain standard deviation right there. From that population, we can take a sample. And each sample is going to have its own sample distribution. So we can take this sample here from the population, and it will end up with a sample distribution. It'll have a sample mean, it'll have a sample standard deviation. If we take a second sample, it'll have its own sample mean, its own sample standard deviation. If we take a third sample, its own sample mean, its own sample standard deviation. So we can take samples from this population and make a distribution of their scores. That's a sample distribution. If we take every single one of these means and put them in a distribution, then we end up with the distribution of sample means. And the distribution of sample means has the same mean as the population, but its standard deviation is the standard deviation of the population divided by the square root of the size of your sample. So importantly, we have 3 different distributions. So when you're reading questions in your homework, when you're doing hypothesis testing, always be sure that you are very clear in your mind. Take a second and step back, take a moment and breathe, make sure that you made that distinction. Are you looking at the population distribution, scores of individuals from your population? Are you looking at your sample distribution, scores of individuals from the sample that you took from your population? Or are you looking at the distribution of sample means, scores of the means of every particular sample made into a distribution, not a distribution of individuals, but a distribution of samples? So when you're working through these next few chapters, keep this slide maybe nearby and handy. Keep these distinctions in your mind, because we're throwing around 3 distributions now, and you got to make sure that you know which one is which. All right, any questions on that? Okay, so that wraps up chapter 4. And what we're going to do right now, because a lot of this right now is conceptual ideas that we need to sort of introduce before we can do any kind of calculations. But what we're going to do right now is we're actually going to start chapter 5. And this is your intro to hypothesis testing. So one of the reasons I'm kind of glad we're ahead right now is that I wanted to introduce this idea and kind of let it sink in, right? This is one of those ideas where you might need multiple looks at it before it starts making, complete sense. So this will be the first of those multiple looks. But now we have finally arrived. So finally, all that work that you've been doing, all that practice, all that sanding the floor and painting the fence, all that work on, waxing off, all of those pre-tests and post-tests and in-class practice and homework and just work that we've been doing to get this stuff as automatic and as solid as possible, all that's going to pay off now. Because now is when we're going to finally start to be able to do that cool stuff, that cool psychology kind of testing where you can decide, is a treatment effective or is it not effective? Does my program work or does my program not work? And this is going to be especially important for those of you that will be doing your advanced lab, because when the time comes, you'll know exactly what to do. And So without further ado, let's get to some of the cool stuff. All right, so we're going to set it up with a hypothetical situation that reflects what you might do if you graduate from here and you become an educational psychologist. All right, so let's say that you become an educational psychologist. Let's say that you go into counseling, for example, and a school calls you up because they need your help, they need your services. So this school calls you up, an elementary school, and they say, we have issues with our school. Our students are suffering from low self-esteem. We believe that something is lowering their self-esteem. We need a way to raise their self-esteem in order to increase their learning outcomes. Please come to our school and see what you can do. So you go to the school and you take a look around, you assess their program, and you notice that they have a very drill-oriented, kind of traditional physical education curriculum. Right? You take a look at their physical education course, and you just see that it's endless push-ups, endless sit-ups, climbing the rope, running laps. And you, with your background in education, pinpoint this as one of the potential causes for the low self-esteem of students. And you go back and devise a treatment program, and you say, all right, what I want to do is I want to replace this physical education program with the traditional drills, and I want to replace it with a games-oriented program. There we go. I want to replace it with a games-oriented program, so they're still getting their required exercise, they're still learning those physical skills, but now in a new kind of setting, a new sort of regime, and I want to see if this is going to raise their self-esteem. And more so than just raising the self-esteem of students in this particular class, we want to know if this program will raise the self-esteem of students across America, students in the population of elementary school students. So that's going to be the question that we're going to tackle. This is your sample, a sample of students at that elementary school that called you up. But again, we're going to ask, does your treatment increase the self-esteem of these students beyond the national average? And also answering at the same time, does your treatment, if it works for these students, does it generalize to the population of students outside of this particular school? So that's going to be the outline, that's going to be the goal for what we're going to take a look at next. We're going to go through the core logic of hypothesis testing. Then we're going to take a look at the hypothesis testing process. And we're going to see this multiple times in multiple different ways. So this is going to be the first time where I'm going to say this, but if this does not make sense today, don't be alarmed. Don't be anxious about it. We're going to go over it again, and then we're going to go over it again. And I'll be completely honest with you, some of you after today will say to yourselves, oh, I get it, hypothesis testing, yes. Others of you will say, what was that? I have no idea what just happened. That's completely fine for hypothesis testing, right? So unlike anything else, you don't have to panic if you don't understand it after today. We're going to see it multiple times. It eventually makes sense. So trust the process, and let's take a look at what this all is. All right, so hypothesis testing. What is this? It's a systematic procedure for deciding whether the results of a research study support a hypothesis that applies to a population. So it is a way, a systematic way of looking at a sample and deciding if what you found in that sample is true of the population. And that's where the power of psychology comes from. We took a look at these 14 individuals, and now we can help these millions. We took a look at this sample of 30, and now we can help, the billions of people on Earth. That's what we're trying to do. And we need a systematic procedure that removes human bias. It removes our own biases either for the treatment or against the treatment. And if you look through the history of science, you will see people pushing their own agendas too fast and just many, especially in the medical profession, many horrible outcomes because people were biased in their interpretation of data. We need a systematic way of looking at this that removes all that human bias. That's what hypothesis testing is. And this is important because researchers, they always want to draw conclusions about a population. So that's one of the first things to remember about hypothesis testing. It's never about the sample. It's always about the population. We use the sample as our tool to get to the population, but it's never about the sample. We're not making conclusions about the sample. We're looking at the sample to make conclusions about the population. So if we're taking a look at the students in this school, we want to draw conclusions about students in general, right? We're going to use the students in the school to make conclusions about students in general. And your conclusions are based on studying a sample, and usually it's going to be a sample of more than one individual. Just so you have a heads up, when you get to chapter 5 in your book, they will start off with a sample size of 1 to just kind of introduce that idea. That's like sacrilegious to a psychologist to do that, but that's their decision. They introduce it in that way. I think it's not correct, which is why we'll kind of go the full correct way from the get-go in hypothesis testing. All right, so what's the core logic? What are we doing here? What's hypothesis testing all about? So, for introduction purposes only, we're going to start off with a population that we know stuff about, all right? Just for illustration and educational purposes, because this rarely ever happens in the real world. So just to kind of introduce the idea, we're going to start off with populations where you know what the mean of the population is, and you know what the standard deviation of the population is. And that's true of some things, like if you were doing a study on IQ scores, if you're doing a study on SAT scores, they have the population data for those scores. So it does happen rarely, but it's easier to understand. What we want to know in psychology is that if we had a treatment that we hoped changed the scores on this population, right? The population is depressed. We have a treatment that we hope makes them not depressed. The population has a certain IQ score. We have a treatment where we hope it'll increase their IQ score. The population has a certain characteristic. We have a treatment that we hope changes that characteristic. That's what we want to find out. So we want to know that if we apply a treatment to this population, will it change into a new population, into a treated population? And this new population will have an unknown mean, and it'll have an unknown standard deviation, because we don't know what the treatment does. That's why we're doing the study. That's why we're looking at this. So this is what we want to find out. Doing it this way would be incredibly unethical. So could you imagine just the horrors that would be unleashed upon this world if science said, you know what, I have a new treatment, let's try it on the whole population and see what happens, right? If it's bad, like most of them are, it was just the human disaster toll would be, through the roof. So we can't do this, right? This is impossible. We can't do this. But this is what we want to know. So what do? We take a sample from that known population. We take a small group of individuals, and we treat that sample, and then we end up with a sample that's been treated, your treated sample. And what hypothesis testing does is it allows you to make the decision of whether or not these people, after the treatment, belong to a new population. Has this sample changed enough that they now no longer belong to the old population, they now belong to the new population? If they were depressed subjects before, and we treated them, are they now belonging to non-depressed individuals? If these were alcoholics before, and we treated them, are they now different enough that they belong to the population of not alcoholics, right? So does your sample now belong to the new treated population? That's what we're That's what the core question is. The sample that you treated, after the treatment, does it belong to a new population? Right? That is the essence of saying, yes, your treatment actually worked. So the last thing we're going to add to this is that for one last assumption here, so for the treated population here, you'll notice that we have no mean. We don't know what the mean of the treated population is, and we don't know what the standard deviation of the treated population is. We're going to make one last assumption, and that's going to be that the standard deviation of the treated population is the same as the standard deviation of the untreated population. And what this means is that your treatment basically moves the scores for the entire population, but it doesn't stretch out or squeeze in the population scores, right? So it changes everybody by the same amount is another way of looking at that. So that assumption there is put in there just to make the mathematics easy. So it's a little bit of a holdover from pre-software, statistical software days, where without that assumption, instead of requiring a stack of papers this thick to do the calculations, you would require a stack of papers this thick to do the calculations. So that one little assumption just makes it very much mathematically easier. That's why it's there, in case you were wondering. All right, so the hypothesis testing procedure. We're going to end with this today, just so that you have like an intro to what it is that we're going to be doing. So the hypothesis testing process, there's 5 steps to your hypothesis testing process. We're going to end today by taking a look at step number 1 in a little bit more depth, and then we'll do the rest of them next time. But step number 1, you restate the question as a research hypothesis and a null hypothesis about the population. Step number 1. Step number 2, you determine the characteristics of the comparison distribution. Your comparison distribution is your distribution of sample means, right? That's step number 2. Step number 3, you determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. This is going to be what I call the lines in the sand, right? This is how weird can a sample be before you refuse to believe it still came from the original population. Step 4, determine your sample score on the comparison distribution. You find out exactly how weird your sample is. And then step 5, you decide whether to reject the null hypothesis. So you'll notice that the null hypothesis pops up a few times. So that's why we're going to end today by taking a look at step number 1 in a little bit more detail. But before we get there, one comforting thought as we go forward on this. These 5 steps here, they are the sort of procedure that underlies the core logic of hypothesis testing, right? So the logic of figuring out if a sample belongs to the treated population or if it still belongs to the known population, that is essentially what these 5 steps do. Importantly, and hopefully comforting, is the fact that if you don't understand this side of it at all, if you're still struggling with the conceptual idea of a hypothesis test, you can still do these 5 steps and do these 5 steps perfectly. So these 5 steps are actual, like, physical kind of things that you can do without understanding this at all. So that's another thing to just keep in mind. You might have no idea what hypothesis testing is all about, but come exam number 2, you can get 100% on it just by following these 5 steps. So it will come, the understanding will come. But in the meantime, just know that as long as you can do the 5 steps, you can do a hypothesis test. So you might not know why it works, but you'll know how to do it. So it's kind of like switching a light on in a room. All you want to do is get the light on. And it doesn't matter if you understand the electrical engineering that goes behind the light, or if all you know is, well, if I flick this plastic doohickey, I can get light. That's what this side is like. All right, so bear that in mind as we go through it. But let's end today with hypothesis testing, the null and the research hypothesis. So first thing you want to do when you're hypothesis testing is you have to make your research question accessible to statistics. You have to let statistics get in there and be able to grab hold of what it is that you're asking. And that's what step one is all about. You restate the question as a research hypothesis and a null hypothesis about the population. So what we're usually asking in general is there a difference between the treated population and the known untreated population? That's what we're asking. Is your treatment effective? If your treatment is effective, there is a difference. If your treatment is ineffective, there is no difference between the population and the known population and the treated population. So, for example, if I said to you, here is the distribution, here's the population of IQ scores. There's your mean IQ, right? For the population of IQ scores. The mean IQ is 100. And I have this new pill. And this pill is designed to increase those IQ scores. And if you give this pill to the entire population, the mean of the treated population is going to be an IQ of 120. So if I was to give my pill to the entire population, the population goes from 100 to 120. If that's the case, you would look at that pill and you would say, wow, that is an effective treatment, right? That treatment is highly effective. That treatment is real. There is a difference between the treated population and the known population or original population. That's an effective treatment. If, on the other hand, I came up to you and I said, all right, original population, 100, right? Mean of the population is 100. That's the IQ score. But if I give them my pill and I treat this entire population, their IQ score is going to go from a mean of 100 to a mean of 100. Well, you would look at that pill and you would say, it's ineffective. It does nothing. Your treatment is useless. Your treatment does nothing. So that's what we want to express in the null hypothesis and the research hypothesis. Your research hypothesis is that the pill does something. Your null hypothesis is that the pill does nothing. So how do we write that out? Well, the research hypothesis is that the treatment does have an effect. Your pill does something. Right? IQ goes to 120. And we write that out as the mean of the treated population does not equal the mean of the untreated population. Right? 120 does not equal 100. That is our research hypothesis. So the research hypothesis is that the treatment does something. The treatment had an effect. And the way that we can write that mathematically is that the mean of that treated population does not equal the mean of the untreated population. If that is true, then your treatment has had an effect. The null hypothesis is the opposite of your research hypothesis. Your research hypothesis is that the treatment does have an effect. Your null hypothesis is that the treatment does not have an effect. And we write that as the mean of your treated population is equal to the mean of your untreated population. So if the mean of the population that took my pill is still 100, 100 is the same as it was before, the mean of my treated population is equal to the mean of my untreated population, that indicates that my treatment has no effect. That indicates that my pill does absolutely nothing to increase IQ scores. So that is where we're going to end it for this, just understanding step one. But that is a crucial aspect of hypothesis testing, translating your question, does my treatment do something, is my treatment effective, into two hypotheses. One, the research hypothesis that the treatment is effective, written as the mean of your treated population, does not equal the mean of your original population. And then the null hypothesis that the treatment has no effect, and that is written out as your mean of your treated population equals the mean of your untreated population. All right, so that's where we're going to wrap it up for today. So we don't got a lot of time left over. This was a mostly sort of conceptual introduction to what it is that we're going to be doing from here on out. But if you want to call it an early day, feel free. If you got questions about anything we did today or anything that we've done previously, feel free to call me over. But other than that, I'm done with what I wanted to cover today.